this PC ไปแล้ว right now it's recording. All right. Howdy everyone. Today I'm going to present you my research that got selected to be funded by the Challenger Fellowship for the next academic year. And the title of the project is Closing the Gaps of Cenozoic Sea Surface Temperature History Using Tetraether Archaeolipid Biomarkers. So what are you going to hear today is about using these beautiful lipid biomarkers that you can see from these vials with different colors, colorful lipid biomarkers for reconstructing the sea surface temperature over the last 66 million years. But before we go into our presentation, I would like to thank the funding agencies and sponsors for supporting me throughout my PhD journey up until now. I would like to thank Fulbright Thailand for supporting me the first 2 years here at the Department of Oceanography, and all the samples that I used for this project for our preliminary results uh, uh, run and tested in our geochemistry lab in our department, and all the samples are coming from IODP. Oh, sorry. And the project just started. It started by just one simple question that my advisor asked me. Did you know that we still don't have a complete record of sea surface temperature for the entire Cenozoic? And for me, who is like not a paleoclimatologist, worked in an oil and gas industry for a couple of years, I have no idea whether that question is true or not. So our first temperature proxies have been developed since 1950s. So my first response to this question is that it should be someone who already have like completed the sea surface temperature records for the Cenozoic. Why not? And things like that. That's kind of question come to my mind. So let's get what I do the first thing after I have been asked this question. I just Google it, and let's just Google it, right? Like it's gonna be an easy way to get an answer these days. So I Google Cenozoic sea surface temperatures, and I see these kind of beautiful charts like all over the place, and it's have a similar shapes in most of the pictures showing up here. So I'm curious, what is this curve, and why Igor just asked me, we don't really have the complete Cenozoic sea surface temperature records. It seems like this is what we wanted to have, right? So first, welcome to Paleoclimate Community Research. So I guarantee you, if you ask paleoclimatologists about Cenozoic climate change, you're probably going to be directed to these beautiful curves, what we call Zarkar's curve. And this curve is the benthic foraminiferal oxygen isotopes over the last 66 million years. And from these charts, you can see that the value of the oxygen isotopes of seawater have been changed from about 0 to heavier and heavier isotopes. It's in more positive number. And when we have a heavier oxygen isotope values is typically or normally corresponding with the colder climates. So from these charts, you can see that over the last 66 million years, our Earth climate is cooling, is continually cooling from Paleocene up to Pleistocene, Pliocene, Pleistocenes, and up until now Holocene. So we have greenhouse climate when we don't really have ice sheet formed or developed it in our polar regions in Antarctica or like Greenland. And that is the time when we have these temperate forests grow in the Antarctica continent. And then when we first have the ice formed, we have the climate state, what we call icehouse climate. And icehouse climate is what we lived in right now, where we have the permanent ice sheet developed in both northern and southern polar regions. So this is the pictures of the East Antarctic ice sheet with lots of cute penguins you can see here. So it seems like what we already have here, it's pretty good already. It's reveal us like the climate history of the entire Cenozoic era. So why we bothering completing the gaps? It seems like it doesn't have any gaps here in this curve. So the problem is that these oxygen isotope data is retrieved or derived from these beautiful organisms living in the oceans, is what we call benthic forams. And calcium carbonate test or shells, whatever you wanted to call that, recorded changes of oxygen composition in seawater over, and it can infer the changes in the temperature. So that's how we know that we have a warmer period and we getting cooling over the last 66 million years. But as the names of these organisms suggest, these benthic organisms living at the bottom of our world ocean. And with our current understanding of how the deep water in the ocean forms, we know that these deep water are pretty homogeneous, and it's formed in certain places in the higher latitudes regions. For an example, on the top panels here is the cross sections of the Atlantic oceans. And you can see that from the northern hemisphere, you have North Atlantic deep water formed in the North Atlantic. And you also have these southern ocean water masses synced and formed as the Antarctic bottom water. Similar pictures, but more homogeneous in the Pacific Ocean basins. Like the entire ocean floor it's in the water at Antarctic bottom water masses. So that could cause the problem for the Sag-Hawkes curve, because what we see in from the Sag-Hawkes curve could mean that it's the changes that happening only in the higher latitudes, and we might miss something from the lower latitudes. So that's like our opportunity to see whether we really have a complete pictures of how the surface ocean changed over the entire Cenozoic or not. Because if the benthic forams only represent the higher latitudes, we still miss a lot of we still miss a large portion of the ocean surface, as you can see from these temperature maps. So the top maps showing you the range of the temperature of the surface ocean, comparing to the bottom map shows you the range of the temperature at the 4,000 meters depth. And you can see that the deep water masses are pretty homogeneous in terms of temperatures. And it's mean that all the benthic forams, even though we collected it from the lower latitudes, it's still gonna shows you similar results from the samples you collected from the higher latitudes, and that's the nature of the bottom water, right? So here is what we have so far in terms of the sea surface temperature records over the last 66 million years. So from these time series plot, on the top row, you have TEX86 data, which I will talk a little bit more in these presentations. And the bottom row is the benthic foraminiferal delta O18, as we already see from the Zaha cost curve. First thing you can noticing right away is that the number of data is much different. And the reason for that is that the benthic data is the global stacked. It means that the data is coming from all over the place, from all ocean basin covering from low to high latitudes. And it's changing in a pretty homogeneous way, meaning that even though sample is coming from different places, it reflects the single water masses, which is our bottom water. Comparing to what we see in the TEX86 data, and now our data was colored by different latitudinal zones. The colder color data represent the higher latitude data, and the warmer color data represent the lower latitude data. And I would talk more in details, but here you can see that it's a few thousands of data points that have been studied and published for these Cenozoic interval, but it's not really complete compared to what we have from these benthic stacks. So that's the first thing. The second thing is that it really reflects the dynamics at the ocean surface. You can see that it's a clear difference between the colder color data points and the warmer color data points, and how it's changed over time over the last 66 million years. And that's what we are going to investigating more in details. So the question you might ask is that we already have these like thousands of data points. Why do we need more data? And isn't it already enough? So as you can see, it's not enough in terms of like completing their entire 66 million years. And it's not, it's the more, I mean, and it's not only we don't really have a complete records, but we don't really have a complete records in a certain latitudinal zone as well. Another problem for the surface temperature is that we cannot do a global stack as the benthic, because if you do a global stacks, you can see that you will definitely not see any trends from these clouds of data points. You have to do it in a latitudinal zones at least, or you have to do it in like regional zones. So that is another layers of problems we have to deal with. Not only we have to fill this gap, but we have to fill this gap with the appropriate samples from appropriate sites. And let me just introduce you a little bit about the proxy I will use, which is TEX86. So what is TEX86 and why I choose it? So I will start it with the why first. So TEX86 is the organic proxies that we use to reconstruct the sea surface temperature over over like several million years in the geological past. And it has been used by a lot of people who studied in a different time scale, even in the Cretaceous, which is dinosaur period, much older than what I'm studying right now. So it have been like proof that it's a good sea surface temperature proxies. And the reason that is good for reconstructing sea surface temperature in the past, especially during the greenhouse climates, is that it's less impacted by the diagenetic changes after it's deposited at C4, which is the main problem for most of the calcium carbonate proxies, where when the shells of the organisms deposited at seafloor, it tends to have the secondary calcium carbonates grow on top of the original shells and make the colder biases to those proxies. Also, it's much less time consuming comparing to reconstructing sea surface temperature from the calcium carbonate samples, because you have to looking for a very well preserved samples for calcium carbonates, but for GDGTs, which is the organic compounds that we use for text edits, is ubiquitous in the ocean, and we can find it everywhere in the oceans. So it's easier to find those materials. It's have some cons for the proxy, like because it's an organic proxy. So if your sedimentary rocks over mature, these organic compounds will be expelled into like hydrocarbons, and it's not there in the rock sequences. And it's a little bit more complex in terms of who produce these biomarkers, because it's relatively new proxy. So it's like an ongoing research about who is the real producer for these GDGTs. But so far, we believe that what we found in the sediments reflects the growing temperature, which is reflects sea surface temperature. So this is how the proxy works. So if you go into the warmer region in the ocean, you collected the sediments and then you extracted the lipids, you will see these pattern of the LC-MS chromatograms. So what you see here is the different organic compounds, which was we call GDGTs. And if you have no rings in your internal structures, you call GDGT zeros, as you can see here. And if you have more cyclopentane rings in your internal structures, you add the number. 1 ring GDGT1, 2 ring GDGT2, and so on and so forth. And from the warmer regions, you will have these high crenocule, low GDGT zeros, and a little bit of these minor GDGT 1, 2, and 3. Comparing to if you collected sediments from polar regions, from the colder regions, you will not really have these minor GDGTs 1, 2, and 3. You will predominantly have GDGT 0, much more than the crenocule. And that's like the main difference between the colder and the warmer water, like the pattern of the GDGT you see from the sediments. And the text 86 is just a simple calculations first proposed in 2002. And it's just a relative abundance between these minor GDGTs. And by calculating these text 86 values from the top sediments, which is the surface sediments that people collecting from all over the global oceans, and compared with the sea surface temperature, you can see that the text 86 values have a strong positive relationship with the sea surface temperature here. And that is the basis of how we can use these text 86 values as our paleothermometer to really measure the changes of sea surface temperature in the past. So our main mission is to produce continuous Cenozoic sea surface temperature records. So as mentioned, there's more than thousands of data have been published, text 86 values from several sites in the global ocean. So why do we still wanted to do it? So this study is not just to add more data into what we already have some already, but what we wanted to do is to fill in the gaps that people haven't had published those text 86 data yet. So most of the studies that have published text 86 values is focusing in the specific time interval in the past. But what we can see here that there are 3 potential gaps that we can fill in more TeX86 data to produce the continuous Cenozoic sea surface temperature records. So my samples is coming from deep sea sediments, and all of the samples is coming from the IODP program, which is the International Ocean Discovery Programs. And here is the pictures of one of the 3 core repositories of IODP houses here at our West Campus. And from these thousands of sediment cores, I have selected few candidates, few sites, and my selection criteria is that I would like to have sites that have a continuous sequence of sediments with relatively fast sedimentation rates, because faster sedimentation rates will give you more materials and will increase a chance of getting enough organic compounds to reconstruct the sea surface temperature. So what we do is that we go collect sediments from the core repositories, we freeze dry them, we homogenize them, we extracted the total lipid extracts, then we purify the lipid fractions we interested in, and then we run it through the LCMS, as you can see here. And you will get the result as you already see as the LCMS chromatograms. And here is the data, the preliminary results from those potential sites that I picked. And from what you can see here, the TeX86 data is the same. The published data is colored from different latitudinal zones, and all the black data point is my preliminary data. And for an example, the data from site 1172 here, it's coming from these southern hemisphere temperate regions, a little bit south of Australia, and it's aligned well with the published data, similar to the site 807 and 929. 807 is in the Western Pacific warm pool, is from the tropics in the Pacific, and 929 is from the tropics in the Atlantic Oceans. It's also giving us similar trends of what the warmer color data showing us, which is more like higher TeX86 values, and it's more like flatter in terms of how it changed over time. So it's promising from these sites that we might be able to fill in these gaps that we wanted to fill in. So that's what we're gonna do next. That's just trying to fill in these gaps. But the question is that after we have the complete continuous records, what we can do with it. So first, we might just simply comparing between what we see from the TeX86 data and the benthic delta 018 global stacks, right? But because the data was very different in terms of like density and like the location they're collecting from. So what I'm doing here is that I'm smoothing the data into like different, using the rolling mean. And then we will be able to compare the value of TeX86 from different latitudinal zones with the benthic delta 018 at each time step across the Cenozoic period. And next is how it's looked like. So before I showed you the correlation between TeX86 value and the delta 018, I just would like to show you, like guide you of what to expect from these cross plot. So the steeper the slope you will see from the 2 proxy could mean that it's the stronger covariation between the 2 proxy. And in this case, TeX86 represents sea surface temperature, and benthic delta 018 represent bottom water. Like we presume that it's represent bottom water temperature. It's mean that if you see these steeper relationship, meaning that what changed at the surface is changing in the bottom ocean as well. But if you have a flatter relationship, it's mean that what changed in the bottom ocean not really corresponding with what changed in the surface oceans. And that's the main thing that I would like to point it out from the data. So here is the results. So from, if you can remember, the warmer data point represent the lower latitude regions, and the colder color data point represent the higher latitude regions. So first thing that we can notice right away is that it's a clear difference between these two regions. Like the green data point is coming from southern hemisphere mid to high latitudes, while the red and orange color data point is coming from tropics. And it's clear that in the tropics, it's much less covariate with the bottom water compared to the southern hemisphere mid to high latitudes. What does these mean? It could mean that like across the entire Cenozoic period, our bottom ocean primarily sources from the southern hemisphere high latitude, which is similar to what we see in the modern ocean system, right? Because our bottom ocean, as we see from the temperature maps and the cross section in the oceans, the majority of the bottom ocean is in the Antarctic bottom water. So that is like aligned with what we expected. But if you see the blue data point, and you might curious what the heck is going on here in the northern polar region, and that is the data from the Arctic oceans, and that is not what that is not out of what we expected, because in TEX86 studies we tend to excluding the samples from the Arctic oceans, and the reason for that is that we still don't really understand the biology in the Arctic Ocean. They might have a different archaea community, which their organic compounds didn't really make the TEX86 value corresponding well with the sea surface temperature. So it's just confirmed that Arctic Ocean is an odd, and it's an odd for the entire Cenozoic era. So what I'm going to do for the next academic year is that I will extract and analyze samples to fill in the gaps I just showed you. And after we have the completed, hopefully completed Cenozoic sea surface temperature records, we can do something more about investigating the thermal history of the ocean surface across the last 66 million years, like how the meridional temperature gradient change over time, and what is the relationship between sea surface temperature and the bottom water temperature, and things like that. So I just would like to end at my presentation by just saying that I hope that I shows you that the global stack of benthic parameter for delta O18 do not reflect low latitude thermal history of the surface ocean across the Cenozoic era. And there are two potential latitudinal zones that we can fill in the TEX86 data to make a continuous Cenozoic sea surface temperature records. And we believe that our completed TEX86 record will inform new perspectives of how the ocean surface changes over the last 66 million years. And that's it. 30 นาที โอเค